Hello, and welcome to the EMC Live webinar, The Future in Radiated Immunity Testing. My name is Dawn Hoffman, and I'm the Marketing Manager at Interference Technology, the creator of EMC Live. EMC Live is a new online 3-day event hosted by Interference Technology. Featuring practical information and topics, this event will include roundtables, webinars, and videos on everything EMC related, and there's no cost to attend. Please join us for our other webinars this week. This webinar is presented by Carl Mueller. Carl is a systems engineer for AR RF microwave instrumentation's radiated and conducted immunity systems and test software. Carl is actively involved in a product and system design, development, and testing, as well as worldwide sales and customer support. This webinar is sponsored by our gold sponsor, AR RF Microwave Instrumentation. AR is your one source for RF, microwave benchtop, and rack-mounted broadband power amplifiers, amplifier modules, complete EMC test systems, EMI receivers, military communications booster amplifiers, and more. The global company consists of AR RF microwave instrumentation, AR modular RF, AR receiver systems, and AR Europe. For more information, visit arworld.us. This webinar is one of many. To check out our others, visit www.emclive2015.com. A recording of this webinar and downloadable PDF will be available on our website shortly. This webinar will be interactive. You will be able to ask questions, and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box in the corner of your screen. If at any time you have a question, we ask you to type in the box and hit send. To make the screen minimize and maximize, click the arrow button. We will present the topic for 35 minutes, followed by a 10-minute question and answer session. Now, Carl will begin the presentation.
Good afternoon. My name is Carl Mueller, and this is what we'll be talking about today. Radiated immunity testing based on the IEC 61000-4-3 standard. Why is radiated immunity testing required? And what changes to radiated immunity testing will accommodate the increasing demands of the future? So if these are the topics you're interested in hearing about, then you have come to the right place. Let's get started. Here's our agenda again. We'll look at the radiated immunity testing in detail, briefly review the applicable standards, compare traditional and future test parameters, including test equipment, calibration, testing, and reporting. We'll look at the trends in electronic devices and what the future holds. What do all the following items have in common? Cars, airplanes, cell phones, GPS, medical equipment. They are all part of our life, and they all require radiated immunity testing. You can ask yourself, why is radiated immunity testing required? Everywhere you turn, electronic devices are being designed to make our lives easier, healthier, and faster. As the radio frequency spectrum is becoming more and more congested, all these electronic devices need to work and coexist with many different radio transmitters. Products and systems must be able to operate in their electromagnetic environment without any failures. They must not introduce intolerable electromagnetic disturbances back into the environment or produce harmonics that interfere with other devices. Here are some examples of electronic products that have to coexist in the same environment. As crazy as it sounds, a car driving next to an airport has to stay running. There have been reports where a car engine has turned off by driving down the highway next to an airport. The cause was the radar pulse signal and used to track airplanes caused havoc to the electronics in the car. There have been power windmills that have malfunctioned because a nearby government radar tracking system was corrupting the windmill controls. If you've ever been in a hospital, you've seen signs requesting that you turn off your cell phone. The problem is that the cell phone can interfere with sensitive medical equipment in intensive care units. There was an incident in a home where a microwave and a cell phone were next to each other. The cell phone received a call and turned on the microwave. Since no one was home, the microwave was unattended and caused a fire. We've all been there, waiting in an airplane for takeoff, when the flight attendant announces, "Please turn off your electronic devices." It seems like an unnecessary inconvenience, but in reality the request is quite real. There have been occurrences where electronic devices have caused minor problems with the function of key systems on the aircraft. Manufacturers like Boeing and Airbus run extensive tests, trying every possible combination to avoid these anomalies. So next time you're sitting on the runway and hear that familiar announcement, just think of this cartoon. However, when in flight, we never know what's happening in the cockpit. The following are just a few applications that are in development now, where radiated immunity testing will be invaluable to the safe operation of the state-of-the-art technologies. In the automotive world, autopilot for your car, automatic speed control based on scanning speed limit signs, and auto assistant parking. In aviation, enhanced guidance system, onboard safety, air quality, and pressurization monitoring. In the office, computers, monitors, printers, projectors, keyboard, smartphones. Green, smart buildings, HVAC control, lighting control, biometric security, air quality monitoring. What is radiated immunity testing? Immunity is the ability of the electronic products to tolerate the influence of electrical energy from other electronic products. It's also called susceptibility. Before a product or system is released into the marketplace, it must be tested for the RF immunity or emission testing. The immunity test method is divided into two categories, conducted and radiated. Four characteristics greatly influence the immunity or susceptibility of the EUT: timing, amplitude, related position or spatial relationship, and frequency. Timing. One example of how timing could influence the EUT occurs when both the culprit and the victim are on. The ease of determining susceptibility then depends on whether the simultaneous operation of the culprit and the victim make their timing relationship appear random, periodic, or continuous. Amplitude. The amplitude of an interfering source energy level determines the susceptibility. The interfering signal adds to the EUT internal noise. If the amplitude of the interfering signal is at the same level as the intended signal, most likely the system will malfunction. Related position. If a EUT is susceptible along a particular axis, then the field generating antenna should be aligned with the axis during the test. It's not a big problem when the test is performed in an ordinary metal box enclosure, but it's an anechoic chamber. Frequency. We'll talk about that on the next slide. For an RF device, there is an in-band immunity and out-of-band immunity, or susceptibility. The in-band comes from the culprit frequency or its harmonics coupling at the victim's tune frequency harmonic, or IF. The out-of-band or non-RF device susceptibility generally results from the culprit frequency coupling into a circuit through an RF response window created by wire, cable, or resonance. Cable resonance is one of the most often occurring problems. Since the frequency response are unknown, the entire RF spectrum must be scanned during an immunity test. Signals can be modulated or pulsed to determine if the system is susceptible. To perform an immunity test, the manufacturer defines performance criteria against which a product will be assessed. These are commonly divided into three categories. The first condition, if the product continuously operates as intended. The second condition, if the product performance degrades. However, normal operation resumes throughout the test with no data loss. Or the third condition, if the product stops functioning or performance degrades and does not recover after the test. There are some guidelines to the following when performing immunity testing. In the test plan, the monitoring method and performance criteria shall be clearly defined. The product should operate in a fully exercised mode. Easy detection of failures. When using a set of matrix rather than a subject matrix, an example of an objective is monitoring a signal voltage that has limits. Example of subjective is monitoring a flashing LED. Here's a list of some of the radiated immunity standards. IEC 61000-4 applies to the immunity requirements of electrical and electronic equipment to withstand radiated electromagnetic energy field. Some examples are consumer products or industrial equipment. DO 160 Section 20 pertains to RF susceptibility immunity testing for airborne equipment for every type of aircraft, from helicopters, business jets, to small general aviation aircraft, to jumbo jets such as Airbus. ISO 111452 standard applies to testing the immunity of electronic components for passenger cars and commercial vehicles. ISO 1145 applies to vehicles. IEC 601-1-2 covers the medical equipment in the emergency medical service environment. Note this standard refers back to the IEC 61000-4-3. All the standards establish test levels and require test procedures. This is a summary of the test equipment required for the traditional radiated immunity testing. A directional coupler is required to measure the forward power with a power meter or spectrum analyzer. Power meter to record the amplifier's forward power that is required to generate the field strength. An RF signal generator capable of covering the frequency band of interest and being amplitude modulated by a 1 kHz sine wave with a modulation depth of 80% and have pulse modulation capability. Power amplifiers to amplify signal and provide antenna drive for the required field strength. EMI filters may be necessary to reduce harmonics. Isotropic field probe and monitor, a field probe to measure field strength. In conjunction with the field probe is a monitor to record the field strength. Note, a receiving antenna or a receiver or spectrum analyzer could be used instead of the isotropic field probe. Shielded enclosures like anechoic chambers or standard metal boxes. As previously noted, radiated immunity testing requires a controlled environment, usually facilitated by an anechoic chamber or TEM cells. Otherwise, the ambient environment could affect the test results, and those results would not be reproducible. The key is to have adequate chamber size to maintain a uniform field. We just covered the test equipment required to perform the radiated immunity testing in the traditional format based on the IEC 61000-4-3 standard. Next, we'll cover the test setup and procedure. The test is broken into 3 functions. Calibration. This is to be performed at least once a year, or if the test setup has been modified. Test, using 1 frequency tone. Test report, created in graphical or tabular format. This is an example of the calibration setup inside a chamber. The field generating antenna or transmitting antenna is located 1 to 3 meters away from the EUT. The field uniformity area is determined based on the EUT's physical size. An isotropic field probe is used to measure the field strength. Optional absorbers can be used on the floor to reduce the signal reflection. The radiated immunity calibration is broken into 2 sections. The first part measures and records the forward power of the field strength required to generate the desired test field strength across the area occupied by the EUT. The goal is to generate a uniform field strength. There are 2 methods to determine if the field strength is uniform. One is constant field strength, the other is constant power. Constant field is recording forward power and constant power is recording field strength. The constant field method is basically recording the forward power while keeping the field strength constant. The constant power method is keeping the forward power constant while recording the field strength. The second part of the calibration is to ensure the amplifier is not operating in saturation by checking the amplifier's linearity, intermods, and harmonics. This is a block diagram showing how UFA, the uniformity field area, is calculated using constant field method. First, you need to pick a start grid point. Using the following steps to measure and record the forward power for each frequency. Increase the forward power until desired field strength is reached. Record forward power. If all the frequencies are completed, then select another grid point and measure the recorded forward power. When all the forward power frequencies are measured for all the grid points, then we are ready to determine the forward power to be used. This basically is measuring the forward power while keeping the field strength constant. After collecting all the forward power measurements for each grid point and frequency, the next step is to determine the forward power to be used per frequency point using the following steps. Sort the forward power reading by frequency of each grid point in ascending order. Start at the highest value and check if 75% of the points are within 6 dB. If 75% of the points are not within the tolerance of 6 dB, then start with the next highest reading. Stop the procedure when 75% of the grid points are within 6 dB. Of the 75% grid points within 6 dB, record the maximum forward power. This is the forward power to be used. This slide shows in tabular data how field uniformity is calculated using the constant field method at one frequency. In this example, 80 megahertz is used and a 16-point grid array is used. Table 1 on the left shows the forward power measured at 80 megahertz for all 16 grid points. Table 2 on the right determines if 75% of the grid points are within 6 dB. Note range 3 has 75% of the grid points within 6 dB. Therefore, you use grid point 11, 35 dBm, for the forward power. This block diagram shows how the UFA is calculated using the constant power method. There are 3 basic functions to be performed. The first is to determine the forward power of the reference grid point per frequency. The second function is to record the field strength. The third, which is shown on the next slide, is to determine the field is uniform. The following are the steps for determining the forward power of the reference grid point. First, select the reference grid point. Next, determine the forward power of the reference grid point per frequency. For each grid point, adjust the forward power to the specified field strength. Record forward power and field strength. Call this the reference forward power. Do this for all the frequencies. After the reference grid point forward power is measured, the next step is to record the field strength for the other grid points using the selected reference forward power for each frequency. Now we are ready to determine the forward power for each frequency based on the recorded field strength. Now you need to determine forward power at each frequency. The following steps walk you through the process. First, sort the field strength reading of each grid point in ascending order. Next, select the lowest field strength as the reference. Using the selected reference point, calculate the difference for all other grid points. Start at the lowest value of the field strength and check if 75% of the readings are within 6 dB. If 75% of the grid points are not within tolerance of 6 dB, then start with the next highest reading. Stop the procedure when 75% of the grid points are within 6 dB. Of the 75% grid points within 6 dB, add 6 dB to the forward power. Use this forward power to set the field strength. This slide shows in tabular data how field uniformity is calculated using the constant power method at one frequency. Again, it's an example at 80 megahertz using a 16-point grid array. Table 1 shows measured field strength for all 16 grid points using grid point 1 forward power of 29 dBm. The last column calculates the field strength related to position 1. Table 2 demonstrates how to determine if 75% of the 16 grid points are within 6 dB. The last column, range 3, shows 75% of the grid points are within 6 dB. The forward power to be used is 35 dBm. That's 29 dBm plus 6 dBm equals 35 dBm. Now we just covered the first part of the calibration. The second part of the radiated immunity calibration involves checking the linearity and harmonics. Linearity. Ensure that each of the amplifier's frequency is not saturated by checking the 1 dB compression of the amplifier. The saturation of the test system is assured by checking the 2 dB compression point with the amplifier and the transmitting antenna. This graph is a plot of the amplifier output power versus the input power. It shows where the 1 dB compression point occurs for one frequency. The diagram below shows the harmonic generated using one tone. The harmonics intermods of each frequency shall be checked and shall be greater than 6 dBc from the fundamental tone to pass. We have covered the calibration portion. Now we'll talk about the test setup and test procedure. Radiated immunity test setup consists of placing the EUT in a shielded enclosure or chamber with a layout that represents its normal operation configuration as closely as possible. Typically, setup includes placing the EUT on a ground plane made from material of the actual environment if possible. A transmit antenna is placed in front of the EUT at a distance specified in the test plan. Typically 1 meter for military applications and 3 meters for other applications. The signal generator and power amplifier are set up outside the shielded enclosure. From here they can drive the transmit antenna and the field strength could be established per the test plan. There should be some type of computer to control the test equipment. The following are the steps required to perform a radiated immunity testing. From the calibration step, set the forward power level to generate the desired field strength. If modulation is required, apply the appropriate modulation. Turn on the signal for the dwell time specified. If the EUT fails, stop the test and lower the forward power to determine the threshold of where the EUT failed. Step to the next frequency and read steps above. Then repeat this for all EUT sides specified in the test plan. The test report shall contain all the information necessary to reproduce the test. In particular, the following shall be recorded: identification of the EUT and associated equipment, any special environment conditions, any specific condition necessary to enable the test to be performed, performance level, performance criteria specified in the test plan, the rationale for pass-fail decisions, any specific condition of use, for example, cable lengths or types, shielding or grounding, or EUT operation conditions. A complete description of the cable and equipment position and orientation shall be included in the test report. We've covered traditional radiated immunity testing. Now we're ready to talk about the radiated immunity testing using multiple tones. We'll discuss how to implement this new test procedure, the required equipment, calibration technique, test setup and procedures, as well as benefits of the new process. Okay, now you ask yourself, how can you generate multiple tones or frequencies to speed up the test? One method is to have multiple setups and radiate the tone simultaneously out different transmitting antennas. This method would be very expensive because you would need multiple signal generators, amplifiers, directional couplers, and transmitting antennas. Another method to generate multiple tones is to have multiple signal generators consolidated into one combiner. The output of the combiner would feed into a signal amplifier. Then the output of the amplifier would feed into one transmitting antenna. This method uses many signal generators and requires a special combiner. Again, this would be a costly design. Another method would be to have one signal generator that could generate multiple tones or frequencies. The output would feed into a single amplifier and one transmitting antenna. This approach simplifies the setup. This method can be accomplished by using a vector signal generator. Remember from the previous slide, the steps during the test are level, apply modulation, dwell, find EUT failure threshold, and go to the next frequency and repeat. Where can you save time? One way is to speed up the leveling process. However, this only saves minimal amount of test time. You ask yourself, where is time spent? The dwell. You could reduce the dwell time. However, dwell time is fixed, specified in the standard. Reducing the dwell time may make tests less effective. A better use of the dwell time is test multiple frequencies at once. This time savings would be proportional to the number of tones used. The chart above shows sample data for frequency range from 80 megahertz to 1000 megahertz with 1% steps. There are 492 steps in this range. The test plan requires testing the transmitting antenna in the vertical and horizontal position, so 2 times the number of steps is 984 steps. If the UT has 4 sides, then you have 3,936 steps. If the dwell required is 10 seconds, test time would take about 11 hours. If you increase the tones from 1 to 4 with a 10-second dwell, your test time will go from 10.9 hours to 2.7 hours. This is a savings of a little more than 8 hours. If you increase the number of tones from 1 to 8 tones during dwell time, the test will go from 10.9 hours to 1.3 hours. This is a savings of roughly 9.5 hours. Think about what you could do with that extra 8 or 9 hours. What benefits you could enjoy. This slide shows all the equipment required for multi-tone radiated immunity testing. Note that the equipment required is the same as for traditional radiated immunity testing, except with the exception of the equipment highlighted in yellow. In multi-tone testing, a vector signal generator will replace the RF signal generator. The vector signal analyzer will replace the power meter, and a high power amplifier will be required. Also, please note that the software will be required to control all the equipment. In the first part of the multi-tone calibration, the uniformity field area will be the same as a traditional radiated immunity calibration. Again, you can either use constant field or constant power method for each tone. This will determine the forward power required for each tone to generate the test level field strength. The second part of the calibration is the linearity and harmonics. This would be different than the traditional radiated immunity calibration. The difference is that you need to establish the sets of tones to be combined. These sets of multiple tones would then be tested for linearity and harmonics using the test levels obtained from part 1 of the calibration. This is a basic flow chart of how linearity is checked using multiple tones. It's broken into 2 major sections: check linearity and check if more tones or tone sets are required. There is an option to start with 1 tone or start with multiple tones. This example starts with 1 tone. Check linearity function based on the uniformity field area forward power from part 1 of the calibration. Use that level to set the forward power. With the vector signal analyzer, measure each tone amplitude using the peak hold function. Reduce the level by 5.1 dB. Measure each tone again. Compare each tone level with the reduced level and must be greater than 3.1 dB. If it passes, then we need to check if you reach the maximum tones per user input. If no, then save the previous tone set. The other section checks if you need to add more tones or tone sets and then retest the linearity in multiple tones. This is a basic flowchart of how harmonics and intermods are checked with multiple tones. Again, this example starts with 1 tone. Check harmonics and intermod is based on the uniformity field area forward power from part 1 of the calibration. Use that level to set the forward power for each tone. Add antenna factors, and with the vector signal analyzer, measure each tone amplitude using the peak hold function. Add antenna factors and measure intermods around fundamental tone. Again, add antenna factor and measure the intermods around harmonics up to the 3rd harmonic. Compare the lowest tone amplitude to the highest harmonic or intermod. Must be greater than 6 dBc to pass. This covers the harmonics intermod check. If the harmonics intermods does not pass, then say the previous tone set. If it passes, then check for more tones or tone set. Keep adding additional tones until required tone set is met or the test fails. This diagram demonstrates how harmonics intermods are generated using two tones. The software needs to set the power level for each of the tones based on the first part of the calibration. Once the power level is set, the intermods around the two fundamental tones will be checked. Intermods and harmonics should not be higher than 6 dBc from the fundamental tone. Next, the second order intermod and harmonics are checked, followed by the third order intermods and harmonics. This table shows the number of tones that can be generated simultaneously in a given frequency range. This is based on the vector signal generator capability to generate tones in 150 megahertz bandwidth. The number of steps in the listed frequency range is based on 1% steps. As you can see, at the lower frequency range, more tones can be generated. The multi-tone setup is the same as the traditional setup. This chart shows the types of time savings you can expect in percentage. This is based on the number of tones and 1% step size. As Ben Franklin said, time is money. If you're able to test even 4 tones in the time it would normally take to test 1, you've saved about 75% of the test time. That equates to savings in man hours as well as more cost-effective use of your equipment and increased throughput and efficiency of your testing facility. As a test laboratory, imagine being able to double or triple your testing capabilities without costly facility expansion. As a manufacturer, imagine the competitive advantage you could have if you could even cut your time to market in half. Reporting requirements will functionally be the same as a traditional. The second part of the calibration, linearity and harmonic test, will show sets of multi-tones and record the worst case harmonic in that set of tones. Linearity for sets will report linearity for each tone and have pass or fail status. Software should provide necessary test information to meet standard as well as documents results in both tabular and graphical formats. This graph is showing how using multitone speeds up the testing when the UT susceptibility limit is above the multitone energy. If the UT susceptibility threshold is below the multitone energy, you can go to the traditional single tone testing, which slows the testing time. After the susceptibility threshold increases, you can go back to using multitone and speed up the testing. In this example, most of the frequency band you can use multitones, which will decrease your test time, especially if you have to rerun the test multiple times. This chart shows how much power is required to generate a field strength of 10 volts per meter at 3 meters using a horn antenna with 1 tone. The data was taken from a UFA data on a horn antenna. 121 amplifier will be required to generate this field strength. With 1 tone at 100 megahertz, 100 watts is the maximum power required to generate 10 volts per meter. At 280 megahertz, using 1 tone, 50 watts is required to generate 10 volts per meter. At 500 megahertz, using 1 tone, 33 watts is required to generate 10 volts per meter. Note, the antenna is more efficient at the upper part of the band, therefore less power, forward power is required to generate 10 volts per meter. If 2 tones were generated, we require 100 watts of average power. At 280 megahertz, using 2 tones, it requires 100 watts of forward power to generate a field strength at 10 volts per meter. Since 120 watt amplifier is used, you have enough marginal power to generate 2 tones from 280 megahertz to 1 gigahertz. Again, it's due to the efficiency of the horn antenna at the upper part of the band. If 3 tones were generated, we require 99 watts of average power. At 500 megahertz, using 3 tones, it requires 99 watts of photo power to generate a field strength of 10 volts per meter. Since 120 watt amplifier is used, you have enough marginal power to generate 3 tones from 500 megahertz to 1 gigahertz. The bottom line is there is extra power available at the higher end of the band to generate multiple tones, again because of the antenna gain at the higher end of the band. This is a summary of the difference between traditional and multi-tone radiated immunity testing. The multi-tone testing requires a vector signal generator, vector signal analyzer, and a larger amplifier than equipment used in traditional testing. I would be remiss if I didn't say that there are costs associated with the additional equipment, but this cost will be offset by time savings. Calibration is also different because you must create and calibrate sets of tones. At face value, this would appear to be time consuming, but in fact, the vector signal generator using a Pixie bus is significantly faster than a GPI bus, so calibration at group levels is actually faster than for single tones. Once you have your sets of tones and have done your calibration, testing can perform rapidly, only slowed for fault isolation. As noted, you'll witness exponential time savings by testing multiple tones simultaneously. Reporting is dependent upon software, but is readily available in both tabular and graphical formats. Recap of the future of radiated immunity testing. The future holds exponential growth in the number of electronic devices required to coexist. Radiated testing is and will continue to be increasingly invaluable. Testing should simulate threats more closely to the real-world environment. With enhanced saturation of frequency ranges, the potential exists for standards changes to reflect the need for more steps, multi-tone testing vital to meet standards as well as reduce test time. The time is now to embrace the future. Using the multi-tone testing allows you more freedom to more efficiently use your time, whether you're speeding up the identification of problems areas during pre-compliance testing or being able to test more thoroughly at a greater number of steps, or getting your product to market faster than your competitors. The key to your future success lies with integrating multi-tone testing into your test procedure. Multi-tone technology has been available roughly for 5 years. You may be asking yourself, if this technique is so innovative, why don't you hear about more people using it? Just take a look at the market leaders across the consumer, automotive, and aviation industries. How do you think they're able to stay at the forefront of their industry? They embrace technology that ensures their future success. The questions are simple. Are you using multi-tone testing? Is your competition? Can you afford to take a wait-and-see approach while others have already embraced the future? The secret to testing multi-tone simultaneously is AR's proprietary software, which is significantly more complex than that for a standard generator. Multi-tone systems are available from AR and contains all instruments needed for multi-tone radiated immunity testing, with the exception of the amplifiers, antennas, and directional couplers, all of which are available from AR but are sold separately. The system contains a field probe, field interface, field monitor, RF switch matrix, and a Pixie chassis which contains the vector signal generator, vector signal analyzer, preamp, and embedded controller. AR's global team of professionals are available to work with you to design a system that's right for you.
Thank you so much, Carl, and I apologize again to the attendees for the technical difficulty that we had. Unfortunately, because of that, we are running up against time. However, we are going to hand it back over to Carl and George Barth, System Project Manager at AR, for 1 or 2 questions.
Okay. The first question I have for George is the multi-tone testing system over-testing the EUT?
The short answer, Carl, is yes. You are exposing the EUT to more energy than you would with a single-tone environment. However, it's probably a more real-world test, and standard does not say that you cannot overexpose your EUT as long as you define a failure as a single-tone event.
Okay. The second question I have for you, will the IEC 61000-4-3 standard allow multi-tone testing? Now, George is on the Working Group 10, which supports the IEC 61000-4-3?
The answer is yes. The 61004-3 will allow multi-tone testing. There's nothing in the standard that says that it's not allowed. And again, we are over testing. Everything in that standard is written to ensure that nothing is under tested, but there's no provision saying that overtest can't be done. Again, failure is being defined as a single tone event. There is work being done on that standard now. Maintenance is ongoing, and in the preparation for the next release, there is also allowances added to that standard, as well as an informative annex added to explain the intricacies and pitfalls and advantages of multi-tone testing and the harmonics and intermodulation products that can occur.
Okay. And last question, what are the limitations of the multi-tone system?
The limitations, Carl, are essentially the amplifier power. Again, if it takes a certain amount of power to generate a certain amount of field at one tone, it takes essentially twice that to do two tones, or three times that to do three tones. The other limitations are the vector signal generator's bandwidth. With a vector signal generator, all of the tones must be within a defined bandwidth, and you covered that as to how many tones you can fit within the 150 megahertz bandwidth of this VSG that we use. The other limitations are it lends itself mostly to substitution type tests, where you can actually set up the test levels and group the signals and do linearity checks. A closed loop test would be possible, but with a closed loop test, you would need to have a frequency discriminating field measurement device like an antenna and a spectrum analyzer.
Okay, thank you.
Okay, thank you, Carl and George, very much. We did receive a number of questions that we will address, and we will notify the attendees when the answers are available. If you have any more questions that we didn't answer here, please send us an email at info@interferencetechnology.com. A recording of this webinar will be available on our website, interferencetechnology.com, and emclive2015.com. We will also send a link to all of the participants shortly. Thank you for attending.